The next talk is by Santiago Pascual. He's a PhD student at the UPC under the supervision of Tony Bonafonte and Joan Serra, and that's about speech enhancement, something. Yep. Okay, all yours.
Yeah, thank you. So today I'm presenting a set of works we worked since Interspeech 2017. So Cgun was the very first work on using generative adversarial networks for some audio-related task, especially in the waveform domain. And everything that derived from there in our group is what I'm presenting here. So it will be framed within the speech enhancement tasks. So I'll first define which are those tasks, what's that application, and then some very quick GAN review. Although GANs have been mentioned, I will formally express what I mean schematically, leaving equations apart for this quick talk. So then I'll talk about speech enhancement GAN and all of those developments, which are Cgun, Cgun+, Cgun transfer learning, WCgun, and whatever. So, and as this is a generative task, rather than bringing you numbers, I'll bring you audio such that you can hear it and evaluate it yourselves. So it will be more dynamic in this case. For such an abstract level of representation, so we will be in the deep layer today. Let's go for the introduction. What is speech enhancement? It's about improving intelligibility and quality of speech in different sets of either distortions or noisy conditions. So you will have some background noise contaminating whatever someone is saying. It's masked out. You want to hear that person speaking, or that person's speech is damaged somehow. For example, he or she cannot speak properly intonating and stuff because of some laryngectomy process, some disease she or he may have. So our motivation to build up the very basics of the work and whatever came afterwards was to build an end-to-end generative model. This was after the GANs boom on 2016, and right after WaveNet appeared. So this was the first application, as I said, to waveform with generative adversarial networks. And why generative adversarial networks? Well, because we wanted this one-shot generation system without slow recursive process. So as Tony said before, the first WaveNet was held slow to generate things because it was auto-regressive. We are not using that. We wanted something to infer some latent representation, clean stuff up, and then recover the clean version in the waveform domain again. And also, we wanted a powerful model that could model all the noisy conditions, speaker identities, and everything mixed up. So take advantage of every data point you have and use it, not separate speakers and stuff like that. And as a final thing that we basically built up after the very first, so the first 3 points are the motivation for the first work, but what came afterwards was just leave noisy conditions apart, now reconstruct speech. So the good thing about this sort of architecture is the versatile behavior it has to take advantage of, okay, you can remove noise, but you can also reconstruct someone's damaged speech. So it's flexible in those terms as well. So we will focus in these two sorts of applications to explain the derivations we made to build the architectures. So for speech denoising, we made something called Cgun and then Cgun+. And then for voice de-whispering, which is recovering someone's intonation or energetic voice. So giving someone vocal folds, okay, let's say it like that. We use the voice de-whispering with WCgun. It's not Wasserstein Cgun, it's whispering Cgun. I just want to state it clear now. So let me first be a bit controversial here. And as we are in a deep learning talk, this fits very well, but this is the classical pipeline for denoising speech, where you had some STFT process here, and you took out of the speech the spectrum domain, you just had the magnitude of your spectrum, and you processed just the magnitude to clean things up, either by masking defectuous bins, like noisy bins, or by regressing, so predicting a clean spectrogram. And then you recovered the signal back by the inverse Fourier transform with the noisy phase, but just processing the spectrum domain because it was easier and well known as good compact features to describe speech. Well, we will go like that. We will just remove those things, and put a simple box, black box, let's say, okay, where I just give the waveform pairs of what I want. And let's see if that works in the waveform domain. So this was one of the first applications of waveform domain with deep learning. And then into the whispering setup, we had the whispered speech, and we used the vocoder, like Tony said. We used vocoder that could extract the vocal track characteristics of someone, and out of that you use a regression model to get the excitation parameters. Then you give both to the vocoder and it reconstructs back the speech. Well, let's do the same thing again. Just put the black box there and see how things work out. So it's a bit controversial for all the knowledge we have, but there is an inductive bias, this word that means I am putting my own prior knowledge into the network architecture by making it as a deep convolutional net, as you will see. Let's jump straight into the generative adversarial networks review, because with this review we will build up what Cgun is. As in generative adversarial networks, what you have is that you want a model generate or model G. You want it to generate some data points that resemble reality. What is reality? Your data points in a database you may have, whether those are images, waveforms, text, whatever. Well, in the case of text, it wouldn't work, but out of the scope of the talk. So we have the generator network, and it maps some random noise, some prior vectors, into something meaningful, structured, that's your data points. So this is learned by by a discriminator saying whether the generated data is real or is fake. Basically, the discriminator is a counterpart to a generator, and the better the discriminator is saying, my input comes from a data set or my input comes from a generator faking real data, then the generator will become better, because both networks' objectives are opposite and both have to optimize themselves to be the best in this game. So by competing, they get better and better. And a good thing about this is we can condition these things. And this is already what Cgun will be, this exact shape. So what's the conditioning factor? Maybe noisy speech or degraded speech. And what has to happen is that the generator has to condense the basic information in that speech and recover it back as realistically as possible to whatever you show to the discriminator. What is a discriminator in this case as well? It's not just about some network saying true or fake. It's like a learnable loss function, okay? As I don't have a clear loss function in mind on how to set these things up, maybe a regression, but it has some lacking properties maybe. Well, let's put a discriminator, and with its simple binary behavior, it's getting rich feature extraction on what is real or what is fake. And by backpropagation, the generator will get better and better and clean things up to pretend it is clean data like the real data. This is the shape of speech enhancement generative adversarial network, which is this. So this is actually the generator, but when we say Cgun, normally this picture appears, and actually this is just G out of the Cgun thing. But yeah, normally we depict the generators, I think. So the important part here is speech enhancement as well. So just let's depict what is doing the enhancement. It's just about inputting some noisy waveform, the full waveform, and a fully convolutional architecture will first encode this thing into a latent space and then recover it back into the waveform domain with the clean shape. Yeah. So the advantage of this sort of architecture, it's processing in one shot all the waveform in the input to get the clean waveform in the output. No autoregressive behavior. And fixed parameters for whatever length you have in the input waveform. So just to mention the few parameters, this is a quite deep model, just let me say that, with 33 layers, 34 if you count jointly generator and discriminator altogether. Generator only is 22 layers, 11 encoder, 11 decoder, because it has to be decimating in 2 by 2 factors the waveform into a latent space, compressing things, and then recovering back the resolution by means of learnable interpolations, 2 by 2. So the thing is, this model was trained with a pretty decent data set at that time, 1.5 years ago, with 28 speakers on 40 noisy conditions. So it was, I think, yeah, 10 different noises and 4 different noisy conditions per noise. The thing is, this already gave some interesting results. You will hear them in a few minutes. But the thing is, we developed it further in a current work we have, especially for journal submission. So this is what we call Cgun Plus. What is it about? First, we gave it a bunch of new data. So from 28, we went to 80 speakers. This already improves the quality of the enhancement. And why? Well, because in deep learning, the more data you have, the better it behaves, especially for Titanic models like this. So with several millions of parameters. And secondly, what we have is the very root of this search in the table, which is very confusing. We just made some sort of ablation study in terms of, I'm just describing it, don't look at the numbers, it's not necessary. Optimization functions, spectral normalization, these sort of things that have been appearing in the GAN community along the last 1 year. The thing is, the very first Cgun model was very hard to make. It was the very first audio GAN model. So in the computer vision community, there was this Cgun as a stable first baseline approach, let's say. But here we had to work out some very tuned parameters to make things work. But as we found out new techniques like normalization techniques and learnable skip connections, we try to apply those, and we actually been importing all those GAN-related techniques into here to stabilize and get better and better results. So Cgun Plus is the result of having a good findings after a huge search. And these are just objective metrics with which we are guided. We have to finally listen to the results to know that this works better, but these correlate pretty well with subjective listening. So either in terms of objective results and subjective results, Cgun Plus is outperforming Cgun itself. So it's basically about this architecture with a reduced set of layers. Why? Because we are way more aggressive in how we decimate and interpolate data. We go from strides of 2 to strides of 4. So this gives us a reduced model. Wow, it's good because it's more compact. And we have a bit different learnable paths like the skip connections path, which turn out to be quite important, and maybe general UNet architectures can benefit from that, from having learnable scaling skip connections. Because that tells the importance of each feature map going from the encoder to the decoder. So you shuttle information, but not just with the identity function, by saying which is more important than the other ones. Other techniques like spectral normalization, which is pretty recent, 3 months ago or 4 maybe, worked very well to make the training more stable and the generator capture more features from the discriminator. This was, after the Cgun and Cgun Plus, what we can, we got to know, and we tried to transfer whatever was doing Cgun in the denoising scheme from English to new languages. And we collaborated with the Korean Chungnam National University such that they brought their Korean data, and we brought our Catalan data, and we tried to transfer knowledge with the least amount of data possible to Cgun, because it's a pretty huge model. So we wanted to check how much data you need in a target language to adapt, even if it's radically different, like Korean and Catalan from English. And it turns out that with less than 3 seconds per speaker, surprisingly, we were doing a pretty decent job in the same level as in the English origin. So we have to depart from some good data set, yeah, like English, with like 9 hours of speech, but then in the target language, you have 3 seconds per speaker, and you train with 10 speakers in the target language, and you have your job done, more or less. You'll hear it now. And you'll see that the first thing that Cgun learns is to respect the new language, okay? And then when you give it more data and more data, it can estimate better what noise to be removed and to be more clear. But first is to respect the speech, which is interesting. And then the last application is the whisper Cgun, W-Cgun, to go from damaged speech speaking in whispers like, hi, I'm Santi, something like that, to, hi, I'm Santi. And here you can note I'm putting some intonation and expressiveness, okay? So you'll feel how end-to-end this model learns to input that without me decomposing the speech itself, okay? So implicitly. But as we had very limited amount of data, clinical data, to do this sort of thing with, in collaboration with researcher from Universidad de Málaga, he handled us the data, but it was a limited amount. We had to add some restrictions. Interestingly, the adversarial setup is so flexible, actually, that you can put more, let's say, sort of conditions on, give it additional fake signals to discriminators such that it can tell whether the content from the whisper input to the reconstructed voiced output changed or not. As you have less data, it might try to just change stuff to generate something like voiced waveforms, regardless of what is being said. Whereas if you impose, no, if you change the content, showing the two chunks, saying the input and the output of the generator, and saying, if this changed, then it's a fake signal, then the GAN captures it and can learn to narrow down the optimization space, let's say. So we had to add this content loss because of the lack of data, which turned out to work pretty well, and the power loss to ensure that the voicing was setting up the proper, I mean, you're imposing now a new energy source. So to narrow down the search of which energy amount to put in the output of G as well. Now it's time for the audio samples and to talk about that this thing is open source. But first, let's see. Oh, no. I have to really? This is not hyperlinked. Anyway, I can do just copy and paste. We'll pretend nothing happened. So you can hear some noise example.
What do we want to do that for?
So there's some music in the background. Now let's see how the best classic bassline does.
What do we want to do that for?
You see there's still noise there. Then a DNN is applied to substitute the spectrum domain in the spectrum domain.
What do we want to do that for?
Okay, still some noise, but a bit better. And now let's go to Cgun Plus.
What do we want to do that for?
And then directly in the waveform somehow it could infer what to be deleted and what not, respecting the speech better than the DNN as results showed. So, and for the whisper case, oh my, here, okay. For the whisper case, you can hear how it reconstructs non-damaged speech. So from the whisper speech,
for the 20th time that evening, the two men shook hands.
then we have an RNN baseline predicting the excitation parameters.
For the 20th time that evening, the two men shook hands.
It sounds robotic and monotonous because this is the behavior of regression models, predicting much more the mean than the variance. Then whisper Cgun.
For the 20th time that evening, the two men shook hands.
You can hear there are artifacts, but now it's generating intonation and expressiveness, given the lack of data we have. And finally, we can hear how it adapts from English to Catalan, having noisy Catalan utterance.
Unes guspires juganeres varen desfer-li tot el gel.
Then Cgun itself, trained with English, does this.
Unes guspires juganeres varen desfer-li tot el gel.
It is destroying the speech pretty much. It never saw Catalan. But what if it sees just 2.4 seconds of Catalan?
Unes guspires juganeres varen desfer-li tot el gel.
And if we give it all the amount of data we have in Catalan?
Unes guspires juganeres varen desfer-li tot el gel.
It just refines getting rid of the noise there is. So finally, oh, there's open sourced, so you can check out to play with all these things, all the prototypes of Cgun. So we've seen an end-to-end flexible speech enhancement system, which can handle many speech enhancement tasks. Cgun Plus, which is an improvement with some ablation studies. The best result we have, and it's published in the repo, the PyTorch repo. And then we checked that it has very interesting capabilities for transferability to new languages. And WCgun is the first approach to reconstructing someone's damaged speech end-to-end. So I think it has potential to do even voice conversion or other tasks of converting speech to speech. So thank you.
Okay, one question. No, can you start setting up your line? Nothing?
Okay. So how does the loss that you had at the end that tried something sounded like the cycle gun at the end that but it was kind of similar. How does it relate to it? Because in the end there was something that you tried to reconstruct the original. You paired the reconstructed so that it doesn't lose the identity.
Okay. So for the pairing thing, I couldn't go much into details, but discriminator is not receiving just enhanced or clean speech. It's getting pairs in the input with stereo input, let's say, 2 channels rather than 1. So it has either enhanced and noisy input to say that's fake, or clean and noisy input to say that's true. So what I add in that case of content is clean input and clean random from the batch, so other samples. So in this case, they mismatch. Both are clean, but they mismatch. The thing that changes is the content. That's also fake signal. It's nothing to do with CycleGun.
Okay, let's thank Santiago again.